Welcome to The Explainer. Today we're going to break down one of the most intuitive ideas in all of machine learning, an algorithm called K-nearest neighbors. At its heart, it's all about a simple, powerful idea we already know. You are who your neighbors are. All right, let's jump right in. Here's a quick look at where we're headed. We'll start with the big idea behind the algorithm, then we'll get into the nitty-gritty of how it actually works with distance and voting. After that, we'll tackle a couple of tricky puzzles you'll always run into. We'll look at a smarter way to count the votes. And finally, we'll wrap it all up with how to use this thing in the real world. First things first, let's talk about the core concept. What's so cool about KNN is that it basically works on a principle we humans use all the time. It's about looking at the company you keep to figure out where you fit in. So let's put ourselves in the machine's shoes for a second. You get this brand new, totally mysterious piece of data. It has no label, no name. How in the world are you supposed to figure out what group it belongs to if you haven't been given a bunch of complicated rules? Well, the KNN approach is, just beautifully simple. To figure out that new point, it just finds a certain number of its closest neighbors. That number is what we call K, and then it pretty much just holds an election. The majority vote wins, and that's the answer. Simple as that. Now, this is what makes KNN so different from a lot of other algorithms. It's what's called a non-parametric method. That sounds technical, but all it really means is that it doesn't try to force your data into a neat box or a straight line. It makes zero assumptions about what the data looks like. It's flexible, and it just adapts to the patterns that are actually there. And get this, it's also what we call a lazy learner. I love this term because it's so perfect. See, most algorithms are eager learners. They do all their homework up front, building a complex model. But KNN, it does absolutely nothing. It just memorizes all the training data and then chills. It doesn't do a single bit of work until the very last second when you ask it for a prediction. It's the ultimate procrastinator of the machine learning world. So how do we take this cool idea of neighborliness and turn it into a concrete process that a computer can actually follow? Let's break down the exact steps. It really boils down to this 5-step playbook. First, you, the human, have to pick a value for K. That's how many neighbors we're going to ask. Then, the algorithm gets to work. It measures the distance from our new mystery point to every single other point it knows about. It finds the K closest ones, checks out their labels, and then, it holds that vote. Majority rules, and bam, that's our prediction. And you can see right here how choosing that K value is a huge deal. It can literally flip the entire prediction on its head. Let's say we want to classify this new green circle. If we pick K equals 3, we look at the inner circle. The vote is 2 reds to 1 blue. The prediction, red. But what if we expand our search and set K to 5? Now we're looking at the outer circle. All of a sudden, the vote is 3 blue to 2 red. The prediction completely flips to blue. Okay, so this brings us to the first big gotcha with KNN. It seems so easy on the surface, but there are 2 critical puzzles you absolutely have to solve to make it work right. Picking the best number for K and figuring out how to make fair comparisons between totally different kinds of data. Choosing the right K is a real balancing act. I mean, how many neighbors should you ask? If you ask too few, you might get swayed by some random weirdo outlier. But if you ask too many, you might drown out the important local patterns. So, where's that sweet spot? It really is a trade-off. If you pick a tiny K, like K equals 1, you get this super jagged, complex boundary that tries to account for every single point. We call that overfitting. But if you go way too big on K, things get smoothed out so much that the model becomes too simple. It might miss the actual patterns in the data, and that's called underfitting. All right, puzzle number 2. And this one is a classic. KNN is all about distance, right? But what happens when your data features are on completely different scales? I mean, a salary of $50,000 is numerically way bigger than an age of 25. When the algorithm calculates distance, that huge salary number is going to totally dominate the tiny age number, making it seem way more important than it actually is. That's a huge problem. So how do we fix this? Simple. We level the playing field. We use a technique called standardization, which basically puts all of our features onto the exact same scale. This makes sure that no single feature gets to bully the others just because its numbers are bigger. Now, age and salary can both contribute equally to figuring out who the true neighbors are. Okay, so we've leveled the playing field for our features. Awesome. But there's another little flaw in the basic system. Is it really fair that every neighbor gets an equal vote? Let's think about that. You know, the basic version of KNN has a bit of a fairness problem. Think about it. A neighbor that is right next door to your new point gets the exact same single vote as another neighbor that's way out on the edge of the circle, barely making the cut. That just doesn't feel right, does it? Let's look at this with a real example. Say we're looking at 5 neighbors to predict if a customer will respond. With a simple vote, we've got 3 no's and 2 yeses, so the prediction is no. But hang on, look closer. The 2 closest neighbors, John and Rachel, are totally split, and the yes from Nora is a lot closer than the other 2 no votes. The simple vote count just completely misses that nuance. This is where weighted KNN comes in. It's a much smarter system. Instead of one neighbor, one vote, we give more power to the votes of the neighbors that are closer. A really common way to do this is to make the vote's weight equal to 1 divided by the distance. So the closer a point is, the bigger its vote. Now, even if the final prediction stays the same in this case, by adding up these weighted scores, we get a result that's way more nuanced and truly reflects who the closest neighbors really are. And this whole weighting system is just so much better. For one, it just makes common sense, right? Closer neighbors should have more say. But it also has this great side effect. It makes the algorithm way more robust. You don't have to stress quite as much about finding the absolute perfect K, because the influence of those faraway neighbors just naturally fades away. All right, so let's bring it all home. We've gone through the theory, the puzzles, the solutions. Now let's talk about the practical, real-world rules for putting KNN to work and getting good results. If you're going to use KNN, you've got to follow a few golden rules. Number 1, and I can't say this enough, always scale your features. It's non-negotiable. It's also a good idea to use an odd number for K, like 3, 5, or 7, just to avoid annoying ties in the voting. And please, don't just guess what K should be. Use a proper method like cross-validation to find the best one for your data. And on the flip side, please avoid these common traps. The biggest mistake by far? Forgetting to scale. A close second is what we call peeking at your test data to pick the best K. That's a huge no-no. It's like studying for a test by looking at the answer key. It gives you a totally fake sense of how well you're actually going to do on new questions you've never seen before. And that really brings us to the core of what KNN is all about. It's this beautiful, simple, flexible algorithm. But it has its trade-offs. It can be slow when it's time to predict, and it can be sensitive to noisy or irrelevant data. It's a fantastic tool, but it's not the right one for every single job. And it leaves us with this final, fascinating question. When is being lazy actually the smartest move you can make?